So we will continue doing problem on rigid body equilibrium. The picnic table has a weight Wt and a center of gravity at Gt. If a man of weight Wm has a center of gravity at Gm and sits down in the centered position shown, determine the vertical reaction at each of the two legs at B. Neglect the thickness of the leg. What can you conclude from your result? Okay. So here, the first step in any problem of equilibrium is to draw the free body diagram. Okay, so here I have a system which is the man of the table. Okay, and the forces acting on this system. I have first the weight of the man. I have the weight of the table, and I have the reaction at the legs. Okay, here you have 4 legs, 2 at A level, 2 at B level, and here we can just see the profile view. So we can say that we have here 2 RA and here 2 RB. Okay, so let me annotate them. So this is the weight of the man, this is the weight of the table, and this is the reaction at A, 2 RA, and the reaction at B, 2 RB. Okay. Now, what we want to do is to check the condition for equilibrium. So to have equilibrium, we will find what will be the reactions at B. They asked for the reaction at B. Who can tell me why here the reaction at B is the critical one? So if I have a very high weight for the man, what can happen?
And the bench would break.
Yeah, I can have tipping over. Yani, if the weight here is very high, I have the risk of tipping over around point A. Then I will lose contact with B. Okay. So now, when I write my relation, I will find what should be the maximum weight of the man to avoid tipping over. Okay. So for this reason, here they asked for the expression at the reaction of B and then to make a conclusion. So to find the expression of reaction at B, the equation that will give me this in directly RB is sum of moment about A. Because when I do sum of moment about A, the reaction at A cannot produce any moment, so I will just have one unknown, which is RB. Okay, so let us write the equation of sum of moments about A. So sum of moments about A equals to, I will take the counterclockwise direction as positive. So I have first for the 2RB force, I multiply by this distance, which is C plus B. So I have 2RB times C plus B. This is the moment of RB. Now, the weight of the table is doing a clockwise moment about A, and I multiply by distance B, so minus WT times B. And finally, I have the weight of the man. The weight of the man is causing a counterclockwise moment. So it is plus W man times the distance, this distance here, which is A. Okay, so a plus W man times A. Now, in order to have sum of moment equal to 0, the reaction at B is given by RB is equal to W man times A minus W table times B over 2C plus B. Okay? So from this equation, in order to not lose contact with B, what is the condition? What is the condition to maintain contact at B? Can you have a negative reaction at B? The support to
Don't
have
we
a
need
reaction,
counterweight?
yes, it should be upward, because to have a reaction between the two, it should be positive. When it becomes zero, this means that you will lose contact at B. So RB should be higher or equal to zero to maintain equilibrium condition. So we deduce that the condition is that W of the man should be higher or equal to W table times B over A. So this is the limit, okay, this is the maximum weight that the table can sustain without tipping over, okay? So here we can see the result, and the conclusion is that to maintain equilibrium, WT, you can do the analysis in two ways, or it depends on what they gave you. Here they gave us the weight of the man, okay? So since they gave us the weight of the man, we can find the condition for the weight of the table, okay? So the weight of the table then should satisfy the condition that so just here, okay, W man, in order to satisfy the condition, we should put here W man smaller, sorry, not higher, okay? While W table should be, so W table, the condition for W table is that W table should be higher or equal to W man times A over B. Okay, so here, since they gave us the weight of the man, we find the condition based on the table. Okay, so W man times, so here this is mine. Okay, W man times A over B. So from here we can find what is the minimum table weight to avoid tipping over. Okay, so here we found out that by replacing W man by its value, that to have RB positive, we should have WT higher than 67.5. Okay? Any question on this problem? Okay. Another problem. The upper portion of the crane room consists of jib AB, which is supported by the pin at A, by the guy line BC, and the backstay CD, and each cable being separately attached to the 2-point C. If the load F is supported by the host line, which passes over the pulley at B, determine the magnitude of the resultant force the pin will exert on A for equilibrium, and the tension in the guy line BC and the tension T in the host line. Neglect the weight of the jib, and the pulley at B has a radius of. So here, in this problem, it might seem a little bit complex. Okay, you have this structure, and I want to find what will be the reaction at A here, and what will be the tension in this cable here, and in the main line. And I have two cables, cable BC. So I want to find what is the tension in BC, TBC. and I want to find the value of tension also in the tension T here. Okay, so first what I know is that the force F acting on the pulley here is equal to 5 kilonewton. So this is 5 kilonewton. Now concerning, I will check if they gave us something about the weight. So when they don't give anything about the weight, okay, I can consider that I have a weightless structure. Okay, so here first to start my analysis, I know one of the forces acting on the pulley. So I will start my analysis from the pulley. Okay, so for the pulley to be in equilibrium, what is the condition? So if I take the free body diagram of the pulley, okay, this is my pulley. It's a massless pulley because they didn't give me any mass. I have on the pulley the action of the force F here. I have, this is F. And from the other side here, I have the tension in this cable, this one. So here, since I have one cable, and then the tension is the same over the cable. So the tension here is equal to tension T. Okay, so here I have a tension T. And of course, since I have my pulley, okay, my pulley is connected to the system, okay, through, and it is connected through point B to AB. So since it's connected to point B to structure AB, I can say that at B, okay, I have Bx and By. So I have forces Bx and By connecting the pulley to AB. Okay, so this is, yes.
هي مش التي لازم تكون equals to F in this case.
نعم.
مش التي لازم تكون equals to F.
بلا بس يلا we will demonstrate this by equation. Okay. Yes, it will be equal. You know why it will be equal? لأنه البولي massless. لو البولي مش massless ما بتكون equal. Okay.
But shouldn't we represent it as one force? أنا هيك قصدي لأنه it's like the same line going through.
Yes, it's the same line بس plus يعني plus إنه it's a frictionless pulley. لو ما كانت frictionless pulley يعني لو عندك يعني هلا when we solve you can say بما إنه ما قالوا شيء بالgiven we can consider it a massless frictionless pulley because it's a massless friction pulley. فيك تقول directly إنه the force is the same along the cable. Yes, you can directly say it's equal to F. أو كمان you can get it from the equation sum of moment about the center of the pulley equal to 0. كمان تعطيك إنه T equal F.
Okay, thank you.
So here you can directly say that they are equal since pulley is massless and frictionless. Or you can put the diagram and from sum of moment about the center, you can say that they are equal. Okay? Plus, we have that this pulley is in interaction with the structure through pin B. Okay? So when we took the pulley separately, its interaction with the other parts here, Bx to B1. Okay? Bx and B1. Okay, now if I consider sum of moment about B, okay, to be 0, هيدي حتعطيني إنه T equal F. So I will again find the same result. If I do sum of moment about 0, I get T equals to F. Now to find Bx and By, I do sum of x equals to 0. And here I have that the forces acting along x are bx and minus f. So bx minus f equals to 0. So bx is equal to f. And also the same for by. So if I do sum of y equals to 0, I get that by minus f equals to 0. So by equal to f. Okay, in this way I got the interaction, the force, if you want, of the joint at on pulley B. Okay, so by equals to f. Now the next step, once I calculated bx and by, I can now move, since I am interested in finding TBC and ax ay. Now I can take my system as جيب AB, okay, plus this small part. So here, if I take AB as my system, what are the external forces acting on AB? So first, I have the pin reaction at A, so it's AX, AY, okay. So here I will take AB plus this small part, okay, together. So here I have that. Here I have the action of the cable. So I have TBC. So AX, AY, and the tension in cable TBC. And by action reaction, okay, by action reaction, I have seen that the effect of the system on the pulley is Bx, By. So by action reaction, the pulley will do on it an opposite reaction, okay? So we have found that Bx on the pulley was to the right, equal to F. So by action reaction, the action on jib AB will be towards the left, equal to F. Okay, and also we found out that By is upward on the pulley, equals to F. So by action reaction, here I should have By downward. Okay, so this is the action, this is the forces acting on AB. Now F is given, so F is 5, I know it. F equals to 5. So I have three unknowns, TBC, AX, AY. Okay, so to calculate these unknowns, I will write the three equations of equilibrium for AB. Okay, so now taking my system as AB, so now my system is AB. Okay, then for this system, I can say that sum of forces along X equals to 0. I have AX minus 5 minus F. Now concerning TBC, okay, TBC, I will decompose it into components. I should find the angle, this angle here. I will call it alpha. So I need this angle to project TBC on X and Y. This angle, I will call it alpha. So how to calculate alpha? If you look well in your figures, I gave you in this triangle ABC. ABC is a right triangle. You have that this distance is A plus B. And this distance here is C. Okay, so you can write that tangent of alpha is equal to A plus B over C. So A plus B is 0.1 plus 1.5, it's 1.6, equals to 1.6 over C, which is 5. Okay, so you can get the value of alpha. Okay. Now, so once I get alpha, I do, when I project on x, it's minus TBC cosine alpha equals to 0. This is the first equation. The second equation is sum of forces along y equals to 0. Along y, I have AY plus TBC sine alpha and minus F minus 5 equals to 0. And finally, okay, I can write a moment equation. If you want here, you could replace one of the forces equation by a moment equation. Because if you do sum of moment about B, you get AY. And if you do sum of moment about A, you can get TBC. So also here, you can do two moment equation instead of one, if you want. Okay. Anyway, you can do this for verification at the end. After finding your unknowns, if you want to verify that your result is true, if you do here sum of moment about B, for example, equals 0. As verification, when you finish, try to verify that sum of moment about A is also 0. So if I write sum of moment about B equals 0, what will be my equation? I have, it will give me, who will tell me it will give me what sum of moment about B equals 0? First, TBC and Bx, By passes through B, no moment. The only force having moment about B is AY. So what can I do?
Multiplied by C.
Yes. So AY times C equals 0. So AY is 0. Okay? Because it's the only force having a moment about A. Okay? So AY is 0. Once I get that AY is 0, I can replace AY into sum of y equals 0 to get TBC, and then replace TBC into first equation to get AX. Okay? And at the end, if you want to verify your calculation, try to do sum of moment about A. You should get 0 if your calculation is right. Okay? Any question on this?
Doctor,
Yes.
I understood the exercise, but for example, why didn't we consider T in the big system? Or we did not even take it?
Look, T, because look, when you take a system and you want to determine the external forces, you should just look at the surrounding, what are the external forces on it. This is the system I considered. And let me clear everything. This is the system I considered. Okay. This is small part here. And this. This is your system. This system is interacting with what? A is a pin, okay? So the pin A is connecting AB to the other, to AC, to AD, A is lumping the action of all on the structure. A is a pin. Because A is a pin, you will represent it by AX and A1, okay? And T here, it's not in direct contact with, if you look at T, it's in this cable. And this cable is in contact with the pulley. So the action of T will be taken into account through the contact with B. And we have calculated together that from contact with B, by action reaction, this force is equal to, in magnitude, to T. Okay? T effect will be here. مش نحن لقينا انه Bx equal to T. So the action of T will be through joint at B. So here you have T like this, and you have F downward. And you already know these values, T and F, from the pulley analysis. You know, T equals to F equals to 5. Okay? So actually the effect of F and T on AB is seen through joint B. Okay?
Yes.
Sorry, can you repeat?
Yes, doctor, thank you.
No, someone else was asking something. Okay. Yeah. So let us continue. Another problem. The mobile crane has a weight W1 and center of gravity G1. The boom has a weight W2 and center of gravity G2. Determine the smallest angle of tilt theta of the boom without causing the crane to overturn if the suspended load weight is W. Neglect the thickness of the tracks at A and B. So here, this idea is repeating, turning over. So always you put your forces. You have reaction at A, you have the reaction at B, you have the weight of your structure here, of the weight here, you have the weight of this force, and you have the weight of your load. So as we said, in general, when we might have a very high load here. If the load is high, here they gave us all weights. The parameter now is theta. So if we increase the tilt angle, we will, we want to find what should be the smallest angle to avoid overtipping. Okay, why? Because here, if I increase my angle, so the variation of the angle will affect the distance, okay, will affect this distance, and therefore will affect the moment caused by this part, okay. So if you increase a lot the angle, what will happen is that the weight of your crane will be dominant, will try to turn over here. Imagine that, for example, if you tilt up to 90 degrees, for example, يعني بيصير كل التقل للتاني مال. Okay, يعني you will have in this case the weight will be just will be dominant from this side. Okay, so if I have a dominant weight from this side, I can have a non-equilibrium condition. Okay, so what I will do the analysis for this configuration. What should be the angle theta to avoid tipping over? Okay, so the first step is to draw the free body diagram. So as you can see here, okay, we considered the free body diagram of the system, and we say that just at tipping condition, so when we will have tipping over, we will have a reaction at A equals to 0, okay, and then we will tip over point B, okay, we'll have tipping over point B. So to do this, what we will do now is that we will calculate what will be the angle theta corresponding to this condition. Okay, so now I have all forces acting on my system. I know everything. Just my condition is to calculate theta. So I will do some of moments about B equals to 0. Okay, then I will do my calculation. So first, what do I have? I have for the weight W1, okay, the W1 is at a distance of B plus C from B. So when I do sum of moments about B, I should consider W1 times B plus C. I will select a positive direction. I consider that the positive direction is a positive, like this, okay. So I have W1 times B plus C for the weight 1. For weight 2, okay, for weight 2, I have the angle is theta, so I should project to find the distance between W2 and B. I should find the projection distance here. Okay, so this projection distance is d times cosine of theta, and just if I look here, maybe it's not clear in this figure. Yes, so let me check if the distance, because I put minus c. Look, to see it well, you should look at it here. Okay, look, d is starting from this point. Okay, so this is your moment. You want to calculate your moment about point B here. Okay, and the distance d is counted from this point. Okay, so when you do d cosine theta, you will calculate this distance from here. But since you want to find the value from B, the distance from B, you should do d cosine theta minus this distance C to get what is the corresponding distance counted from B, because you are doing sum of moments about B. Okay, so here concerning W2, it's a negative moment because W2 tends to rotate your structure in the clockwise direction. Okay, so this is why and as we considered the counterclockwise as positive, so it's minus omega 2 d cosine theta minus c, while for the weight of your load, it's the same procedure, but now you will do, so here this distance here is counted from this point is d plus e cosine theta, and then since you want to find the distance from B, you should subtract C, so it's minus w times d plus e cosine theta minus C. Okay, so this should be equal to 0. Okay, in this way you can find the critical angle theta which will cause a tipping over. هلا هن in the question here you should pay attention. بالجواب اللي عم بيجيبوه هن ما عم بيجيبوا minimum angle، عم بيجيبوا maximum angle، لأنه انتبهوا في two conditions للtipping. You can have tipping over B, you can have tipping over A. So when you have here, when you increase theta, what will happen يعني هون when you decrease theta إذا بدكم، كل ما صغرنا theta كل ما زاد المومنت in this way. okay، وصار في ساعتها probability of losing contact with A. بس إذا نحن بدنا نجيب مش المينيمم انجل، الماكسيمم انجل، بتصير القصة بالقلب. يعني ساعتها التيبينج اوفر ما بيصير around B، بيصير around A. يعني انتم اذا هلا بس in practical cases نحن ما راح نكبر تتا ليصير على تاني مال ويقلب الستراكشر about point B. اوكي، بس هن السؤال تبعهم غلط. لازم يسالوا what is the minimum angle theta to not have tipping over، مش the maximum